So the next topic we're going to cover, really the final topic when it comes to iterators, is random access iterators. So as the name implies, a random access iterator allows algorithms to randomly access the elements in a container as long as that container exports random access iterators via its begin and end factory methods. And there are really only a couple of predefined STL algorithms that provide random access iterators, and those are vectors and decks. And you'll get a chance to build a random access iterator for assignment 4, so it's important to pay close attention to what we're talking about here. So you'll see that random access iterators basically give you all the benefits of pointer arithmetic, the full-fledged capability of pointer arithmetic. And so if you think about this as a hierarchy or a pyramid, then random access iterators are at the apex of that hierarchy. And what they do is they implement everything that a bidirectional iterator implements, plus they also provide support for plus equal and minus equal. They provide support for plus and minus. They provide support for the relational operators like less than and greater than, less than and equal, greater than and equal, and so on. And of course, they also provide support for the subscript operator, in addition to everything else that we've talked about. And we'll go through this more when we get into the code examples. So we've got a couple of examples illustrating how random access iterators work. And so what I'll do at this point is switch over and talk about those. So as you can see here, we're now in the part of my example. This is the 4.7 family of examples, 4.7a, 4.7b, 4.7c, and so on. And they're going to demonstrate the use of random access iterators. And as we'll see, they give you essentially the full gamut of capabilities that pointer arithmetic provides. So arbitrary offsets, subscripting, subtraction, addition, plus, plus, minus, minus, and so on. So basically, they have all the operations we've come to know and love with bidirectional iterators, which of course, in turn, have all things we've come to know and love with forward iterators and so on. But then the random access iterators can also do all of this other stuff. So as you can see, there's a lot of other stuff. So we're going to take a look at how you can use a vector and a random access iterator for vector. And we're also going to see how you can do the same thing with a built-in C-style C++ array. So first, we're going to show pointer arithmetic with the built-in C++ array, and then we're going to show how to use the same thing with random access iterators to a container. So here you can see we've got a built-in array, A of int, and we've got a bunch of numbers, and they just happen to be sorted. And I kind of do this on purpose. You'll see why in a second. And then we're going to define ourselves a local variable called total even, which starts out with the value 0, and it uses C++ type deduction. And then down here, we're going to use a for loop to go from the beginning of this array to the end of the array, up to but not including the end of the array. And every time through, we're going to go ahead and sum the total values, but we're going to skip over the odd numbers. So we're going to start at location 0, which has 0. We're going to store that value. Then we're going to go and do a plus equal to our pointer. And of course, this is, under the hood, this is actually int star. That's what it really is. When you say auto here, it turns into int star. And so what we're doing is every time we do IP, which is our iterator pointer, plus equal to, we're skipping over the odd numbers. So we're going to basically add up 0, 2, 4, 6, 8, and then of course we're going to be done. And then when we're done, we'll print the sum of the even numbers, which will be whatever it is. So that's the way we do this with just good old-fashioned pointer arithmetic. Down here, I show you how to do the same thing, except this time we're using a vector instead of a naked built-in array. So as you can see here, we have a vector of 10 numbers, 0 through 9, and it's basically the same algorithm. The main difference is that we're using auto int iterator, and this, of course, under the hood is actually going to be vector int iterator. So that's what it's actually doing under the hood, but that's a bit too verbose, so we just say auto, and then we're going to go ahead and start at the beginning and go to the end. And so this is just another way of being able to make this all work. Now you can see here, if we really, really want to be sort of, source code compatible with the two implementations, we could, instead of writing v.begin and then v.end, we could actually say begin v and end v. And now the code really looks like the code up here. The one difference, of course, is we can't say a.begin. You can't do this because it's not a class, it's not an object, so you can't access its methods that way. But this is kind of cool. So now you can write this really generic code that just doesn't know or care at the source level whether or not it's dealing with some kind of user-defined type or predefined STL type or a native C or C++ style type. And once again, we're going to total up all the even numbers and skip over the odd numbers. So notice how we're using the pointer arithmetic mechanism plus equal to skip through the iterator. And when we go ahead and compile this, we get the expected result. The values all sum up to 20, both for the array version and also for the vector version. So that's pretty cool. Once again, underscoring the uniformity and kind of principle of least surprise capabilities that you get with C++ STL. All right, so now let's go ahead and take a look at the next example here. And this is going to be a little bit more kind of funky. And the reason it's more funky is we're just going to demonstrate a bunch of pointer arithmetic style operations using random access iterators. So here we're going to start off once again doing things with our built-in array first, just to demonstrate pointer arithmetic before we show how the random access iterators from vector let you do the same thing. So here we're going to go ahead and make ourselves two pointers. So I is a pointer and J is also a pointer. So I points to the beginning of array A, and then J points to the beginning of array A plus 2. So that'll point to value 3 here. And then we go ahead and print the value of J. So we indirect through it by dereferencing that iterator, which is just a pointer in this case. And then we go ahead and perform some pointer arithmetic. So we take I and we scoot it ahead by 3. So it's going to basically point to the end. So we'll print out 4. And then we're going to go ahead and take I and subtract 1 from it and make that J. So now we move forward a little bit and we print that. And then we take J and we minus equal 2. So that scoots it back to the beginning again. And we go ahead and print that. And then we just print A sub 1 just to demonstrate we can do that. And then over here, we're going to go completely bonkers and do some relational comparisons between these two pointers. So J less than I, remember we're comparing pointers now, and we print out what the right relationship is. And then we say J greater than I, and again, we print out the right relationship. Then finally, we assign I equal to J, and then we do some other comparisons, which should indicate that I and J are equal at that point because we assigned J to I. So this is all just kind of classic C-style pointer arithmetic. And then down here, we have our vector, and we do exactly the same thing. In fact, I probably, if I really want to be consistent with this, let's have a little fun here just to demonstrate even more consistency. I can come along and just say this. So now we create a vector that has the values 1, 2, 3, 4. So that's really pretty much identical to what we did up above with our built-in array. So now we do it with a vector. And then down here, we do pretty much the same thing. In fact, I guess if I really wanted to be consistent here, I could have said, begin A, which would have given me back an iterator to the array. And then down here, just to be, 100% syntactically consistent, I could say begin V. So once again, notice this cool begin helper method works the same for built-in arrays and containers. And then henceforth, everything else here is pretty much identical to what we had above. So we go ahead and we store those values, and we update the various iterators. We print out the results. We do comparison operations. We assign the iterator j to iterator I, and then we do a check for equality and so on. So let's go ahead and run this code, and you can see what we've got when we're all done. Should basically be the same. So we have 3, 4, 3, 1, 2. That's the same for both of these. You can see that I is less than j. You can see that it's not the case that j is greater than I, and then after we do the assignment, then I and j are equal. So, so pretty cool stuff. Hopefully that gives you a good, warm, fuzzy feeling about the fact that the pointer arithmetic mechanisms available with normal C and C++ built-in arrays work equivalently when you use random access iterators on sequential containers like decks and like vectors. Probably should have shown a deck example, but it's the same thing. So it wouldn't have added anything to the mix other than just changing the data type from vector to deck, but you get the same behavior. Okay, so here's yet another example of demonstrating these kinds of things. And in this case, we're going to have an array of character string literals. So A, B, C, D, E, F, G up to J. We go ahead and print the results out using the copy algorithm. So that works out quite nicely. And you can see here, I use string. I probably could also use const char star, which is even, it's also going to work the same way. And then I go ahead and I set my array. I make it sort of an iterator. So I make this pointer called P, which is treated as an iterator. Then I go ahead and plus equal it 5. So now it refers to the 5th element in the array. So that's 0, 1, 2, 3, 4, 5. That's F. And then I go ahead and take the 5th element, and then I subscript it by 1 more. So now I go and change the value 1 beyond that. So that should now have the value Z. And then I go ahead and scoot back the P pointer back to the start. And then I go ahead and copy from beginning to end. And so all I have to do here is just say P and end A, and then that'll go ahead and print the results. So that's how we do this using good old pointer arithmetic. Now let's go down and see the same thing, except we're going to use C++ STL. In this case, we're using vector. Let's go ahead just for kicks and change this to deck. Probably have to change this to deck. So I'm getting tired of using vector for everything. So just to demonstrate, no tricks up my sleeve, I just changed vector to deck. Everything should continue to work as before. Again, just for kicks, let's go ahead and do this syntax just to make it look more like the version above. So there you go. You can see we go from beginning to end. Once again, we're going to go ahead and take a look at the beginning iterator, and we store that in P. We can increment that. We can subscript through it. We can decrement it. And then we can go ahead and print the contents from beginning to end. So that the source code here, aside from the fact that we've got a deck as opposed to an array, it's the same basic content. And let's go ahead and run this code, and hopefully it'll work, which I think it will. And you can see what the results are. So the results here in both cases are going to be identical. They're always going to do the same thing, showing yet again the consistency and swappability of built-in STL types with the algorithms we're looking at and the pointer arithmetic syntax, and using C++ containers with random access iterator semantics. So what I want to do to kind of wrap this thing up is just put this in perspective. So the iterator mechanism provided by C++ is very canonical, very standardized. It looks just like pointer arithmetic for the most part. So chances are at some point you'll have to write a class, you'll have to write your own C++ class where you need or would like to provide iterators in order to be able to plug your class into all the cool STL algorithms. And in fact, that day is coming shortly, because the next programming assignment will give you a chance to do that. And so there's a nice article you can read at the link below that kind of talks about implementing the various types of iterator semantics and talks about some of the subtleties with things like post-decrement and pre-decrement and const iterators and so on. And so the good news is that writing your own iterators is pretty straightforward, although to be honest with you, it's rather tedious. So it's something where you have to spend a lot of time like niggling with minor details in order to get everything working correctly. You have to figure out what type of category to support, random access, bidirectional, and so on. You have to figure out how to handle the differences between pre-decrement or pre-increment and post-increment operations, and pre-decrement and post-decrement operations. And all of those things are just a little bit tricky, but they're not really hard, they're just subtle. And so it'll take a little bit of doing. If you take a close look at STL implementations, you'll see that they have their own kind of generic iterator class. It's kind of a template class. I think it's called something like __ normal iterator. And then a lot of the iterators in STL just use the templatized iterator to make their iterator implementations because they're all very canonical. For your implementation, you'll actually have to implement it yourself by hand to get practice with this, but realize that in production systems, they eat their own dog food, and they use templates and reusable abstractions in order to implement a generic iterator that's then used to implement all the other iterators that are part of STL containers.